As we start chapter 9, oh yes, I have been grading the submission on the normal, not normal. If you just realized, oh, junk, I didn't submit something last night by midnight and you have it done, just email me a copy ASAP. Second thing, I have not even started looking at the exams yet. Just haven't had the time. But hoping to get to that either this afternoon or tomorrow. You know, that's what you do for fun on Saturdays. And then, yeah, we'll be revisiting some of the second exam content. I'll describe that later. But for right now, we're jumping into 9. 9 is getting us to a question that I'd actually asked a couple sessions ago, where we looked at, hey, once we figure out all this stuff and I do a confidence interval, what if my confidence interval doesn't include what I think it should? So that's kind of where we're going to start with this with your groups this morning, is take a look at this information based on what we've covered up till now in this class. Can you put together a reasonable response to the question being asked with, does this evidence support or reject the NIMH, National Institute of Mental Health, claim for this particular town? So, with your groups, turn, talk, start to brainstorm. I would have had you at the boards with markers, but I've been really good lately at leaving them at home. So, doesn't do me any good here, nor you. So, you're just going to have to actually turn and talk to each other and see if you can create an answer to this question. There you go. So we got P hat and Q hat. What else do we know? Yes, sir?
Find the error.
Find the which?
The standard error.
Standard error. Okay. So standard error, when we're talking about proportions. All right. In this case, since we don't know actual P and Q, I'll use P hat, Q hat over N. That's standard error formula. All right. And did anybody calculate out what that value is? 0.0346. All right. So standard error is another one of, and I heard someone studying the other day, there's like a million different ways to calculate standard deviation. Yeah, because it all depends on which scenario you're talking about. So standard error of P hat is the standard deviation of all the possible P hats that we could take from this little town. So if you did another sample of 100 from this same little town, and then another sample of 100, and then another sample of 100, and then and I do that like a lot of times. This value is approximately equal to the standard deviation of all of those P hats. So each P hat would be, on average, about 3.46%, right, because it's out of 100, away from the actual P, the actual proportion of people in this town who suffer from depression or depressive illness. All right, but that's just refreshing our memories on what actually is this number. I mean, numbers are great, don't get me wrong, I'm a math teacher, but understanding what they mean, far more important. What else? From anything that we've talked about or discussed in this class to this point, could we do? Ooh, sorry about that. Wrong button. When we're doing sampling, one of the biggest questions we're going to come back to is the distribution of all the p-hats approximately normal? So this is not a central limit question, central limit theorem. Right? The CLT says if I have sample sizes of 30 or more, and whatever I'm measuring about those samples, right, quantitative values, so if I'm looking at the means, all of the sample means would follow approximately a normal distribution if my sample size was over 30. Here I'm not measuring anything, I'm just counting. Either they have the depressive illness or they don't. So that's why I said it's binomial. They do or they don't. So in this case, we can't use the 30 when looking at the sample size. So instead, we have another characteristic that we look at.
It has to be more than 5 successes or failures.
Yes. So NP must be at least 5, which is another way of saying that is I must have at least 5 successes and I must have at least 5 failures. Is that true? How many successes do I have? 14. Now again, remember I said success and failure is not a emotional thing, right? Because we're saying that someone who is suffering from depression or depressive illness is a success in this scenario. So success is the number of things I'm looking at and counting. I'm looking for people who are depressed. There are 14. 14 is greater than 5. Do I have more than 5 failures? Yes, there are 85 people who do not have depression or depressive illness. 86 failures. That's greater than 5. Therefore, and this is very important to say on all problems that we're going to be working on, once you discern and determine normality of a sampling distribution, you need to say that fact. First, you show it right here. Some words would be good, even though I didn't put them on here. But because I'm recording this and you can hear my voice, it's the things you'd be writing down. Since there are 14 successes, and that's greater than 5, and there are 86 failures, and that's also greater than 5, therefore, the sampling distribution of p hats is normal or approximately normal. I usually say approximately. Is approximately normal. You didn't want to move it all up. Let's shrink it down. Give myself some more space now. The distribution of p hats will be centered at p, the actual proportion, which I don't know what it is. Or wait, do they tell us what it is? Yes. It's supposed to be 0.095. So p is the center, and they say the actual proportion of people who are depressed or have depressive illness is 9.5% or 0.095. I had a p-value or a p-hat value of 0.14, which on my normal curve, I can go 1, 2, 3 over here, 1, 2, 3 over there. This number, the one that we started with, that 0.0346, that's the standard error of p-hat. That's the standard deviation of p-hats. That's the distance from here to there. That's one standard deviation. So if I wanted to, I could write that number in there as, what's 0.0346 plus 0.099? 0.1196. I took 0.95, which was the center number, because they tell me it's 9.5%. I added one of these standard deviations to it to get 0.1196. Now that assumes that I could add correctly in my head. Not always the most trustworthy thing to do. But that would be one standard deviation. So my value of p hat here is probably right about there. Ballpark. Like I'm sort of guessing, but a smart guess. So is that above average? Yes. Is it a lot above average? Depends on how we define a lot. But if we go with information and concepts that we've covered up till now, now that we've done this, we've said, okay, we've determined my p hat and my q hat. I've determined the standard deviations of my p hat. I've figured out and determined that the sampling distribution of p hats is normal. What is something else we've done up until now? We have constructed confidence intervals. All right. So I could do the same thing here. I could construct a confidence interval. All right. From the generalized formula that was on your formula card, it's statistic plus or minus critical value times standard deviation of the statistic. So in words, it's statistic plus or minus the critical value times the standard deviation of the statistic. So in this case, my statistic, my sample value, because a statistic is something taken from a sample, my sample value is p hat. Plus or minus, we'll come to CV in a second. Standard deviation of the statistic, that was the standard error of p hat. It's that number over here. But then I got to decide on, I meant to use my pointer tool, the critical value. The ones that we've used so far are either Z or T. So then you have to remember, is this a T test or a T scenario, T procedure, or is it Z? And when we're doing proportions, proportions are always Z. And then we plug in numbers. Oh, do we have a percent? We were not given a percent. What's a common percent that we use a lot? 95%. So if I do a confidence level of 95%, I could either remember 1.95996, because I've done it a bunch of times. If you used approximately 1.96, that would be okay. If you don't remember that, you pulled up the normal applet, which automatically comes up to Z. In the little red box for area, you would put, because 95%, this is 95. The rest is 5, so this would be 0.025 in that tail area. You'd put the 0.025 in the little red box on the applet page. Now, if you're not using that applet page on a regular basis when you're doing the problems out of the book, you should be. Verify all those numbers that we're getting as we're working through this so that you're comfortable using those websites regularly. So p hat is 14 out of 100 plus or minus 1.96 times the standard error, which we calculated. And then what I would do is I would go to Stat Blue. So if you don't have that open already, pop that open. Our Stat Blue website. And if I remember correctly, it is the third section over. Maybe the second, I want to say it's even green. It's green, yep. And it says confidence interval for a proportion. If you click that button, it takes you to the screen. It asks you for n, which in this case is 100. It asks you for p hat, which for us is 14 out of 100 or 0.14. Confidence interval we selected to be 95%. And then lastly, you hit calculate. And what does it give me as a result for my interval? .072. That's, I'll just go with 072. What's the upper number? 0.208. Did everybody else get those same values? I see a couple head nods, which is good. So up until now, we've said that I would indicate I am 95% confident that the actual proportion of American adults who suffer from depression or depressive illness in this town would be between 0.07 and 0.21. Or 0.07 and 0.21. Or 7.2% and 20.8%. Is that consistent with the National Institute of Mental Health's published article? The answer is yes. Why do we say yes? Because 9.5 is in my interval. It doesn't matter where it occurs in the interval. And that's really important because some of you will want to say, like if it were let's say it was 0.073. You're like, oh, but that's barely in the interval. Like if the National Institute, instead of 9.5, it was 0.073, 7.3%, you would say, oh, but it's right on the edge. That doesn't matter. If it's in the interval, anywhere in the interval, we say that we are at a 95% level of confidence going to not disagree with the 9.5. Okay. I'm not going to say it is 9.5. I'm just going to say I don't disagree with their statement. 9.5 is possible, a possible percentage of individuals in this town who have a mental depression or depressive illness. All right. And it gets back to, so I just got my jury summons yesterday. Yay. Go serve on jury duty. But in court, you have two options at the end of a court hearing. Well, typically two. I mean, you could have something thrown out. But essentially, you have either they're guilty or they are acquitted. You cannot prove that someone is not guilty. All they say is there is not enough evidence to prove guilt. Are they guilty beyond a reasonable doubt? No. There's a reasonable doubt in there. Does that mean they didn't do it? Nope. They may have done it, but they couldn't prove that it happened to a reasonable degree. So that's why I say when we're looking at this, that 9.5, it's reasonable because it's in my interval. My interval does not say that it is 9.5. It just says that it could be. 9.5 is a reasonable assumption based on what I did for my sample. So with a binomial, this is refresher about what we just did. So in case you're like wondering, like, what did we just do? We just said that the average of a binomial is n times p. The standard deviation is the square root of npq. But then down here, the p hats will follow a normal distribution when the np and nq are, when we have 5 successes, 5 failures. where it's centered at P, and the standard deviation is PQ over N. And then we took the square root of it. All right, so that's what we just did. I have it on there as a slide, just so in case you couldn't read my writing on the previous stuff, that's what's going on. But by the end of this chapter, so we're going to take what we just did today here just now, and we're going to extrapolate that into what this next chapter is all about. And this next chapter is about hypothesis testing. So by the end of this chapter, you'll be able to differentiate between a type 1 and a type 2 error. You'll be able to describe a hypothesis test in general, and then we'll do it in practice. You'll be able to conduct and interpret hypothesis tests. That's the biggest thing. For a single proportion of the mean, when we know the standard deviation. For a single population mean, when we don't know the standard deviation. And then also for a proportion. And it will be consistent in the fact that if we do know the standard, if the standard deviation is known, we're going to use a Z procedure. If the standard deviation is unknown, we're going to use the T procedure. And if we're doing it with a population proportion, we're doing a Z procedure again. So the component, here's just a quick outline of the components. Today we're going to actually talk about errors. We're going to talk about hypotheses. All right, as we get rolling with this. So, when we have a hypothesis test, much like the court case, we have two hypotheses, and this is getting more to the language of statistics. The two hypotheses we have are the null and the alternative. All right. The null, we denote it by H sub naught. Naught is a fancy name for, zero. It's not the letter O. H sub naught. It's the null hypothesis. And the null hypothesis, I'll put a colon after it. Never put an equal sign after this, please. That would be mathematically inaccurate because the null hypothesis is not a variable. All right. The null hypothesis, sometimes you consider it our status quo. It's what we've known to be true. In that example that we started with, we said the National Institute of Mental Health said that the proportion of individuals who have depression or depressive illness is 0.095. All right? So it's the status quo. It will always be a parameter. Again, drawing on language from earlier in the term, parameter is our statistical word that means a value about an entire population. Parameters, populations, P. Statistics are then like X bar and P hat. Statistics are from a sample, S and S. Statistics, sample, population, parameter. All right. So that's our null hypothesis is what we've known to be true. And you're going to have opportunities to read research articles for much of the rest of your academic careers. And you're going to see these things being referenced, especially the further along you get in your coursework. Where if you're anywhere in the social sciences, psychology, sociology, that kind of arena, you're going to see it happening where they're talking about different aspects of how people behave and what happens and results. But it also could be from more of a clinical side of things too, where you're getting medical experiments that are going on. All right. Math and science, you're going to be seeing it more from a quantitative point of view where you're looking at, does this improve that? What are my, I think of concrete, the different aspects of concrete, does this new additive consistently or significantly improve the structural integrity of this concrete by adding this whatever thing to it? But the status quo is what it used to be. If it used to be this, then we're testing to see if it's better, worse, or just different. What we're testing for is the alternative hypothesis. In the court system, in the United States anyways, the null hypothesis is that you are innocent. Innocent until proven guilty. So our alternative hypothesis is what we're trying to prove. And what we're going to be starting with for the most part is we're going to be looking at probably 3 different things that we're going to try to prove. We're going to try to prove that something is increased, decreased, or it's different. So in the example that we did already, the question was, hey, is this town consistent with what the National Institute of Mental Health said? So what we were trying to prove is the proportion of those with a depression or depressive illness different than what the population says? If it's different, then that would just means it's inconsistent. Or if we think one town is like happier than another town, we'd say, hey, maybe they have less, or the town is more depressive. All right, Cleveland, depressing city. For me, some people like it. All right, some of y'all are not from Reading, and you think Reading's depressing. It's actually not. It's the land of happiness. Thank you for the chuckle. All right. So the null hypothesis is what the status quo was. It's our background. So we're going to have P equals something, or I'm going to have, if I'm measuring something, mu equals something. Down here I'll have mu not equal to, or I'll have something in the alternative hypothesis where it's mu greater than a value, mu less than a value. So let's go like this. If my null hypothesis was mu equals 25, I could have down here mu not less than 25. The other thing about the hypotheses is whatever this number is in the null, it'll be the same value when we're writing it in the alternative. Okay. What I cannot have in the null and alternative hypotheses, cannot have p hat, cannot have x bar. P hat and x bar are the samples we're going to take to see if they match with what the population was supposed to have been. So while you're working on those, I will do this one. J. All right, my first group that I'm going to go to are the 3s. Where are my 3s? There's one of them. Where's the other 2? Oh, that it? Just the 2? And then behind you is Dominique. Were you a 3? Okay. So 3s. A, B, or C? Which one do you want to do? C. So tell me what you would have written. The null is what? Mu equals 100,000. All right. Then what? All right. Some of you might be looking at that word that says at least, which if you've been trained in the past means greater than or equal to. For us now in a hypothesis test, we don't care about it being greater than or equal to. The equal is always on the null. So this one would just be greater than. All right? And yes, that's correct. Fives. You want to do D, E, or F?
We'll do F.
F. Go ahead.
For the null, mu is equal to 10, and then for the alternative, mu is less than 10.
Okay. The mean number of cars that someone owns in a lifetime is not more than 10. Not more than is the same as less than. So yes. Jax. Do you want to do G, H, or I?
I'll do G.
G. I mean we.
For the HO, I put the mu is equal to 1/2. And then for the alternative, I did mu is greater than 100.
All right. It's not average. For G, it says about half of the Americans. So that's a percentage. So instead of mu, I use P. For a population proportion is 0.5. And then what'd you say the alternative was?
Greater than.
P is greater than. Prefer to live. Yep. So given the choice, it would be prefer there'd be over 50%. That's honestly one of the harder ones to figure out, because prefer is like, well, what is like? Is that more? Is that less? So if we're looking at how many would do, but then here again, the example that what we just talked about is in this case now we're doing proportions because it says half of. So anytime we're talking about percentage in terms of how many, we use P. The only time that I can think of that we would use percentage where that might be actually a mu is if you're doing like something in a chemical, like a chemical concentration. So there, a chemical concentration, the percentage is actually measuring something, like a percent of hydrochloric acid. All right. In this case, we're counting people, so that's a percent, so we use P. So that's the confusing sometimes part about using percentages. Yes, sir. I. A little bit louder, sorry. P is equal to 0.11. 0.11, yeah. So it's given as a percent, but I'm going to use decimal in my mu and my alternative. And then my alternative will be, no, P is less than 0.11. Is under 11%. That's less than. Yeah. All right, hopefully getting the hang of this here a little bit. Sevens. E. P is less than 0.05. So hopefully as we're doing a couple of these, we'll do one more. Twos. B. It's going to be the other way around. At most 60% means you're less than 60%. All right. So hopefully you're getting kind of the hang of this for what you would do and what you would insert there for the null and alternative as you're working through that. And then lastly for today are errors. All right. So getting back to court for a second. Null is they are innocent. Alternative, they are guilty. There should be an L in there. All right, so when we do a hypothesis test, we have 4 possible outcomes. We either are going to, we're going to either say that we prove HA and we're right. We prove HA, the alternative hypothesis, and we're wrong, right? So if someone really did do something and the alternative is you proved them guilty and we did it, that's just success. if we prove the alternative and we say they're guilty, but they really didn't do it, that is what's called a type 1 error. So if you prove the alternative and you were wrong, that's a type 1 error. Another way of saying that is if I'll come back to that one. Let's do the other two. So then if we don't prove the alternative and we're right, that just means we were accurate. Like the alternative, we were not allowed to prove it and we were right about it, we're good to go. If we don't prove the alternative and we were wrong, that's a type 2 error. So, and that's just kind of what they are in general statements. Our book, other books, myself included, I might say it differently every time. And that's not meant to cause confusion, but more to create the fact that there's just many ways that you can hear it. So if I repeat it different ways, hopefully you start to connect how those are related. So what do I mean by that? If I prove the alternative, I'm also rejecting the null. All right? So if I prove the alternative, another way to say that is I reject the null. If I've proven they're guilty, I've rejected their innocence. If I cannot prove their guilt, so I did not prove HA, I do not reject the null. And now here's a phrase I want you to strike from your mathematical mind so that you never say it ever. You can never, mathematically speaking, ever say, I accept the null. You are guaranteed to get all the previous work wrong if you say you accept the null. Much like on the last exam, when we're doing confidence intervals, if you said there's a 90% chance that the mean is in this interval, that is 100% wrong. There is not a 90% chance that the mean is in an interval. In the same way here, you can never accept the null. You can never actually prove someone is innocent. I mean, there might be no evidence at all to their guilt, but that in no way proves innocence. It just means I really don't have any data, information, or reason to believe they're guilty, but that doesn't mean they're innocent. All right? I'm sure many of you went to high school with that one kid who seemed like they always did the wrong thing but never got caught because they could never pin it on them. You knew they weren't innocent. But that principal could never prove their guilt. Some of you are thinking, that's me. All right? They all thought I was just a sweet person going through high school. Little did they know, I was a turd. All right? So, if I reject the alternative, I do not reject the null. But I do not accept the null. If I do not reject the alternative and I'm right, all right, so there's two ways that you can be right, and there's two ways you can be wrong. And the two ways you can be wrong are different ways about being wrong. And depending on the scenario, one of them will have a worse outcome. So if we look at these here, we'll just take a look at this first one. The mean number of Americans work before retiring. Sorry, the mean number of years Americans work before retiring is 34. Now, we know this is not actually true because I would been retired a long time ago. All right, but what this wants you to do is, okay, if this were the scenario, so this is the null hypothesis. So in this case, my null was that they're 34. And since they don't say more, less than, anything like that, my alternative would be that they're not 34. But what this question is asking is, state the type 1 and type 2 errors in complete sentences given the following statements. So in a complete sentence, and I'm going to use, when you're doing an interpretation of the errors, don't use the words null, don't use the words alternative. But I'm going to talk about it as I start to write it. So here's my alternative. This is what I'm trying to prove. A type 1 error is I say that this is true and it's not. So in a sentence, I would say, there is evidence to prove that the average age of retirement isn't 34, but I was wrong. So there was evidence for it based on the sample that I did, and somehow later on I figured out I was actually wrong. And that is a type 1 error. You'll find that the way you write a type 2 error is going to be very similar. So the type 2 error, we'll do it down here at the bottom. There was insufficient evidence to prove the average age of retirement wasn't 34 years, but I was wrong. So a type 2 error is I did not reject the alternative, and I should have. All right, so type 1, I reject the null, I accept the alternative, and I was wrong in that process. Type 2 error is I did not reject the null. I did not reject the null, and I did not accept the alternative, and I was wrong. So I want everybody here, before we leave, take a look at, we'll go back to this one, F. Take a moment, talk with your partner sitting next to you, write a complete sentence for each type 1 and type 2 errors, and then as before, I will draw a random card and call on one group to read me the alternative, or type 1, and another group to read their type 2. So take a minute, write that down. All right, so the type 1 is that the average number, there is evidence to prove that the average number of cars is not more than 10. My alternative would be mu is less than 10. So the type 1 is proving the alternative. So there is evidence to prove that the mean number of cars is not more than 10, but I was wrong. And that's a type 1 error. Type number 9 is type 2.
There is insufficient evidence to prove that the mean number of cars per lifetime is less than 10, but I was wrong.
There we go. There's insufficient evidence to prove that the mean number of cars in his or her own lifetime is less than 10, but I was wrong. Yeah. So there you go. That's your welcome to Chapter 9. For the record, I'm at 12 so far. Vehicles in my lifetime. Please leave your cards on the desk on your way out.